Picking up where we just left off in section 4.2, we've got a new value. This thing's going to be called E. This thing, E, is going to be an irrational number. And there's actually two ways of writing it. Once I get this erased, I will show you all the other method of getting E. So you can either write the limit as x goes to 0 of 1 plus x raised to the 1 over x, or any guess what the other one is?
Yeah.
Or you can rewrite it as the limit as instead of y or instead of x, I'm going to use y now. I'm going to use t. As t goes to infinity of 1 plus 1 over t raised to the t. So you can write it in either way. We're actually going to use this after a while. This is going to be useful to us later. Why is that? What's happening here that makes this work?
Are you saying, what's the difference between your limb with infinity and the limit with 0?
Well, that's exactly the question I was just asking. What is the difference? And when does this work?
Well, one has a t, one has an x, one has a 0, one has an infinity.
It's the 0 and the infinity that's really different, right? Because here we're just saying, instead of calling this x or y or whatever, we're just going to call our variable t.
Mm-hmm.
If x goes to 0, this x is going to go to 0, and this whole thing, though, 1 over x, that's going to go to infinity, right? Now, looking down here, when t goes to infinity, this 1 over t goes to 0, but this exponent goes to infinity.
So it's opposite.
Exactly. They're just really, they're the exact same statement, just flipped. Makes sense? So all we're doing here is we're using a substitution. The difference between these is that t is equal to 1 over x. That's the only difference. They are the exact same statement. We're just making a substitution here. And like I said, this comes in hand after a while. This is a handy thing to observe.
Are they both equal to E?
Yes, they're both equal to E. Does anybody want to guess what that E value is?
Irrational numbers.
It is an irrational number. So what does that mean? What does it mean for it to be an irrational number? So good question to start off with. What's a rational number versus an irrational number? Y'all know? A rational number is a number that either repeats, like 1 over 3, right? When we write it as a decimal, it's 0.3 repeating. Or it terminates. So there's only so many digits in it. An irrational number neither repeats nor terminates. So for example, pi. There's no repetition in the decimals of pi. And it doesn't terminate either. There's no end to pi either. It's just a long number with decimals that never repeat themselves. E does the same thing. It's a long number with decimals that don't repeat themselves. They don't ever end. So this is what it means for it to be an irrational number. And just to give y'all an idea of what E is, it's approximately 2.718. Now, another question about this. looking at this, can you all see why it might be useful? What happens when you take the derivative, raise this to a power, and take it, the derivative with respect to that power? What happens in here? This is the hint for why we're even talking about this, because this is going to be where this is all heading in a minute. Right now, just to get an idea of what E is, what it looks like, blah, 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 blah. E, functionally or graphically, looks just like any of our other positive bases raised to an exponent, right? Numerically, like I said, it's about 2.718. It's a non-repeating, non-terminating decimal. In the limit, as we go to infinity, or negative infinity, e raised to the x is going to be equal to 0. If we were to change the sign on this and make it infinity, it would go to infinity, which we can kind of see here, right? This thing goes off to 0 in this direction. It goes off to infinity in this direction. At 0, e to the 0 is still equal to 1. I don't know why they have an approximation here, because it's not approximate, it is equal. And it shows up all over the place. One example is in what's called logistic growth functions. A logistic growth function graphically looks about like this. And now, let me ask, does that function look familiar? This second one, does it look familiar? I argue that it damn well better, or you haven't been paying attention to anything for the last year and a half.
Year and a half.
Yeah. This function, this graph, should jump out at you right now. What's going on in the last year and a half that it might jump out at you?
Work from home rate.
Well, this is some data that's relevant to what's going on. That is logistics. These are all logistic curves. They have that same general behavior. What the hell am I talking about? What is this data of? Any clue? Yes. These are COVID hospitalization data points. So as an example of why you should give a damn about this class or any math class, this is literally dominating your life right now. This one function has dominated the last year and a half. It is why India is finally starting to see their rates starting to tamp down a little bit. It is why every time we opened back up, we saw increases in rates. It is why every time we shut down, it took time for the rates to decrease. This single function shows up all over epidemiological studies. Anything that's a disease is going to in some way, shape, or form be modeled by this function. What this function is doing is it's saying you have a population that could experience a disease, for example. This is the example that we're using right now, so let's keep going with disease. You have, let's say, 100,000 people who could potentially catch disease. But as more people catch that disease, fewer people remain who can catch that disease. So the rate at which people catch that disease starts to decline. Because it starts to decline, you get this sort of behavior where it increases pretty quickly at first. And we have this point of inflection somewhere in here. And it starts to decrease in the speed at which people catch the disease. And it steadies off onto a steady state. This function uses the exponential. It uses e, right? It shows up in other places in biology. For example, population growth studies will oftentimes see this. So let's say we're talking about China, and there might be, for whatever reason, some limit in the amount of food that that nation can hold forever, right? Maybe there's only 12,000 units of food. As the population grows and food becomes more scarce, population of people would take on this behavior. This function shows up everywhere. And because it shows up everywhere, I personally think it's one of the highlights of this class. It's one of those things that I should be like, this is what you should care, obviously.
I like outside of the
So what?
like outside of
Yeah.
the
Dope. Well, the subject's just cool, right? This is one of the things I want you all to walk away from my class with. It's not a fear of math, but this understanding that math isn't adversarial. Like it's not a subject that we're supposed to have to fight with. It's something that is really more of a tool, a description of what's going on around us. It exists before we ever put it on paper. And because it does, like I said, it's not adversarial, it's descriptive and helpful. It lets us see into problems that we wouldn't otherwise be able to understand. But it also demands a lot of work from us, as does most things that are worth doing. Your degree is going to require a lot of work from you. Just like a math degree would require a lot of work. It's no different. Anyhow, the place that this thing comes from, that this function comes from, is what's called a differential equation. It's this differential equation. I'm not going to really go through how it's derived. This is just an aside, but it does show up all over the place in population studies, in growth rates, in the capacity at which you could maintain something. Maybe you're talking about, maybe you're a company with so much storage space and you're trying to store, I don't know, crude oil. If you're selling your crude oil at a particular rate and you are producing crude oil at a particular rate, this function will show up for a way of how to model how much crude oil you can store at a particular point in time. It could show up, I should say. There's all sorts of different things. So, getting into what this class is actually about, getting back to these problems, and getting back on track. Let's say we have this model that predicts how much a culture is going to weigh as a function of time. So you've got this culture, a little petri dish. It's got some agar in it. And on that agar, you got bacteria growing. Those are fuzzy patches of bacteria.
Of course.
This function models the growth of a particular bacteria, and what it tells you is the weight of that culture as a function of time. So what we're saying here is, well, the amount of area that you can grow into, that's bounded. And as you grow, there's less area. So you start to grow slower. And as you grow slower, you experience this logistic curve, right? And that's what this thing is doing. It's saying you can only grow so much, but as you do, because less and less area is available, you start growing more and more slowly. And the question here is, at 0 hours, what does this whole thing weigh? At 1 hour, what does this whole thing weigh? At 10 hours, what does this whole thing weigh? And when will this thing weigh 1.5 grams? So at 0, we would plug in 0 for t. So this whole thing becomes 1 plus 1 plus 0.25 in the denominator, so 1.25 in the denominator. And we're going to divide 1.25 by that. So at time 0, y is equal to 1. So the agar and the petri dish together just weigh 1 gram. At 1 hour, you're going to plug in 1 here. That's going to come out to be whatever that is. At 10 hours, you're going to do the same thing. And at 1.5, you're going to set this equal to 1.5 and solve for t. So looking at this, we start off at 1 gram. We get to 1.071 grams after 1 hour. After 10 hours, we get to 1.244 grams. And as time goes on to infinity, the most that this thing can grow, look at what's happening here. This is going to shrink, right? Because it's a positive number greater than 1 raised to a negative power. You're letting that power grow to infinity. So this is going to go to 0 times 0.25. Well, that's still 0. Plus 1, well, that's going to be 1. So 1.25 divided by 1 is going to come out to be 125. Make sense? Another place that these exponential functions show up, that each and every one of you should know. Please, 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 do not leave this class without understanding this. And I say that because all of you have student loans, and this is what dominates your student loans. This is compound interest and continuous interest. This is what I want y'all to walk away from my class understanding, because this will dictate a good chunk of your life. A good chunk. Student loans are ridiculous in cost, and the interest rates are crazy. This is how you're going to figure out what you're going to owe in the future. So, having said that, when calculating the amount of interest that occurs over a period of time, what you're going to do is you're going to start off with your principal amount, P. You're going to multiply that by 1 plus the rate of interest divided by the frequency of how it compounds. So if it compounds annually, the frequency is 1. Excuse me. If it compounds semi-annually, the frequency is 2. Quarterly, it's 4. Monthly, it's 12. Daily, it's 365. Now, question. What if it compounds continuously? What's happening here? As time gets more and more continuous, and gets bigger, right? It's approaching infinity. Agreed? So if we want to know what continuous, what it would look like for interest to compound continuously, we could logically ask what it would be if n went to infinity, right? That makes sense in this context, agreed? And that is exactly what it is. You take the limit as n goes to infinity. Well, we can pull out this p. And when we do, we can make another move in between here, between these two steps. What's happening is we're saying the limit as n goes to infinity of p times 1 plus r over n raised to the n. This is equal to the limit as n goes to infinity. I'm going to say p times the limit as n goes to infinity of 1 plus r over n to the n power. Now, we're going to divide out in our exponent an r. But when we do, that means we also need to multiply our entire thing by an r as well, right? What I'm saying is, we're going to come over here and we're going to say, let's factor out an r in our exponent. But we can't just factor out an r because that changes everything. So we need to also multiply our exponent by an r. So let's play multiply by 1. Agree? In other words, and do this. Say, cool, we got p times the limit as n goes to infinity of 1 plus r over n times n, the r over r. So this thing is going to be equal to p times the limit as n goes to infinity of 1 plus r to the n, r over n raised to the n over r times r. But we just had a rule in that last section that we can pull this r apart from everything else, right?
What's the difference between the top and the black, the left one and the right one? Is there anything different? Oh, the
You see-
limit, yeah,
I just
yeah.
pulled out p.
Okay, no, you're good. I'm like, well, okay, we're good. Continue.
So now we've got this rule about exponents that lets us say, let's pull out this r. Let's do it in a special way. We're going to say the limit as n goes to infinity of 1 plus r over n raised to the n over r. That quantity raised to the r. Now, let's take another moment to look at what we've got. We could rewrite r over n as being equal to x. But if we do, when n goes to infinity, then x has to go to 0, right? So we're going to change our limits now. We're going to say, so this thing then is p times the limit as x goes to 0. We got that from this. Of 1 plus x. Well, this thing, this is just going to be 1 over x, right? So let's replace that exponent of n over r as 1 over x. That whole thing times r. Well, lo and behold, What we just got is a limit definition of E. So this has to be equal to the principal amount times E raised to the R. This is the function for continuous compounding interest.
Just like regular compounding interest, it seems easier.
Yeah, this thing's actually easier in the end, once you simplify it.
Once you simplify it.
And I wish I was back in.
It's a good movie. It's a good reference.
I would just have to do it all in my head. Actually.
Nobody can.
You don't think that's the reality?
There's some things you can do in your head, like you can approximate values, sure. But you've got 2.718 raised to a decimal. You're not gonna do that in your head. Because this is the 10/8 root of a value. Like, don't even try. Like, it doesn't, no.
So you say I can do it all in calculus.
With things like this, yes, absolutely do it. Do it with a calculator, do it in pen and paper. Obviously on an exam, I want you all to show your work in the end. So, I don't think I ever went back and looked at your work, did I?
How did we show you our work?
I
Submitted it to Blackboard. That's why I forgot. The announcement got sent out late. That's why I didn't do it this time around. Okay.
Oh, yeah, because I had never known how to do that. How do you submit it?
There was just like a separate
Yeah.
exam word tab.
Oh, yeah, I completely did not see that at all.
That's all right. I just talking about the exam work
Exam work.
just reminded me of it. And
Oh,
I didn't do that because I forgot. I didn't forget. I accidentally clicked the wrong Friday for the announcement to get sent out.
Mm.
So it got sent out the Friday of the exam that explained like what the expectations were. That won't happen this time around. But anyhow, getting back to this problem. What this is telling us is that after a year, if you have a principal amount of $1,000 that is compounding continuously at 8%, the amount after a year will be $1,083.29. And what's happening here is we're first converting this percentage into its decimal value,
Yep.
0.08, and raising e to that and multiplying it by the initial principal amount.
there is an E on my calculator.
There is. Most calculators, even non-graphing, will have it. So this brings us to the two different formulas for compounding interest. You have compounding n times a year and compounding continuously. Now, having said all of this, notice T here. T is going to be the amount of time in years. It is the amount of time, I say again, in years. And I make this distinction because if I told you that I wanted you to calculate something over 43 months, well, that's 3 point something, right? That's not 4, that's not 46, 43, it's 3 point whatever that comes out to be in the number of years.
Is that just in compounded continuously?
That is both,
That's both. T
Yes.
is used for both.
yes.
Okay.
these two equations are going to show up all throughout your life. Anytime you touch buying a car, buying a house, your student loans, mortgages, insurance, this shows up all over the place. Insurance in a much different way. There's a whole long other thing about that. But these two equations, walk away from this class with them seared in your mind with a general understanding of what the hell's happening.
I think I learned that in algebra 2. Is that
A,
I think econ. It was new.
you should see it in econ. It should show up in algebra. It would make sense. If you'll get a chance, there's a class here called Contemporary Mathematics. It is an alternative to taking algebra, but it's math that's applied. Like the entire class is about where you will see it in society in a day-to-day sense. So you go through doing taxes, you go through calculating things like interest rates, et cetera, et cetera. It's a good class for just like, this is math and where you're going to use it in society as far as like expectations of where it'll show up.
you teach that?
Like annuities and CDs. I have taught it once.
Did you like teaching it?
It was a fun class, actually. I did enjoy it. I actually just had a student last week and walk up to me and tell me that he was his favorite math class. I was like, yes, I will take that. All right, so as an example of where this problem might show up, let's say we deposit 12K into an account that's going to be incurring interest in different ways. So you deposit 12K on the day of somebody's birthday. It matures till they turn 25, and at 25, they can access it. And you're trying to figure out which one of these four possibilities is best. Yes, which account, which setup is going to work out best for, in this case, your nephew. So, because again, we just saw the different methods of, the different formulas, I'm just going to jump right to this problem and show the solutions. At 7% compounding continuously, you got 69K out of that. So 12K turned into 69, that's not a bad turnaround. Compounding quarterly, you get 68K, that sucks. Compared to that continuous compounding. At 11%, you get 187K compounding continuously. And compounding quarterly, you get 180K. So continuously, obviously, the better bet, right? Better bang for your buck, unless it's interest on a loan. If it's interest on a loan, you would prefer quarterly compounds, right? Excuse me. However, if it's something like a CD, you would prefer continuous compounding. Notice also the difference that 4% made here. That is huge. Huge, huge, huge. I have a loan, a student loan at both of these values. And they compound continuously. These make huge differences. Just 4%. That is a difference of 0.04 in values, right? You got 0.07, 0.11. That's how these two rates compare. That is giant, though, when it comes to interest rates. Effective interest rates, I'm going to jump through a lot of these just because I want to get to other stuff in this material. So there is this other question of present value. present value is solving for principal, essentially. You're saying, I have the amount, I know the amount of time, how much do I have to initially deposit? That's what you're asking for when you solve for present value. So you're just solving for P here. Is that cool? And the question essentially comes down to, let's say you have a CD. You go to the bank and you tell Elizabeth, hey, I want a CD that in 5 years will be worth 5K. You know, in 5 years, you want 5K. Elizabeth tells you, all right, we've got CDs that have these particular rates of interest. Maybe one CD has a rate of interest of, well, usually the way this works is the rates of interest and time are related to each other, right? So a CD is going to be a certain amount if you want it to mature in 5 years versus if you want it to mature in 10 years versus so forth and so on. They do change those. But you said you want it at 5 years, and she said, all right, cool. The CD that we offer at 5 years has a rate of, let's say 3%. Is that realistic? I don't know.
Not right now, no.
No. What are they right now?
Everything, 5 years, but I think for us is 0.85.
Percent?
Yeah. You know what yours are?
Also similar, they're pretty low. They make it a
0.85?
little bit hard to knock it off.
I think 4 years, or no, 3 years is 0.65. It's really bad right now.
All right, so
You don't
right now,
want-
if you go to a bank
You don't.
and you want a CD that matures in 5 years,
Cool.
it's gonna have a rate associated with it of about 0.85%. So I'm being told by the bankers in the classroom right now.
Yeah, they're both colors. with
So-
different things.
So you sit down with Elizabeth, you say, all right, I want, like I said, 5K at the end of 5 years. She says, cool, well, the rate here is 0.85%. Say, all right, how much do I need to pay then? What do I need to put down as my deposit to make sure that this happens in 5 years? She says, all right, well, I know how to calculate the amount based on the principal that a interest will incur, right? So we have the principal amount, the initial deposit, and A here represents the amount owed or the amount accumulated over some period of time T that get measured in years. She said, well, we can rearrange this. We can divide both sides by this, right? And solve for P. Bada bing, bada boom. This is what we get. We say, cool. So if I want 5K at the end of 5 years, then the amount that I need to deposit is going to be 5,000 divided by 1 plus the rate 0.8. My mistake, 0.085 divided by, wait, how often does this compound? Well, let's say it compounds quarterly. I would just assume that's probably what most of your CDs are compounding at, right? Quarterly rates.
I think ours are monthly.
Monthly? Okay, cool. No, let's do monthly. 12
If you can pull out of it monthly.
Well, times,
You get interest.
you can pull out of your CD monthly?
You can pull out the, you can pull out
That's
the interest that you
weird.
earn. So some people like.
Why would you do that? Because that devalues the amount you're gonna get in the long
Some
run.
people just live off of like the interest that
Oh,
they pay on
yeah,
CDs, so they would just pull back out. What
Gotcha.
they spend for that month.
So, looking at this, the amount that you're gonna have to deposit today, assuming your CD compounds interest monthly, so 12, over a period of 5 years, and at a rate of 0.85%, it's gonna look like this. Could one of y'all type that into your calculators? I don't have one. It's gonna be a stupid number. I'm gonna guess it's 4 something. It's gonna be a high 3,000, low 4,000.
Did you say stupidly low number?
High.
Oh,
I
okay.
got 47.92.
That sounds right. Cool. 47.92, you said?
I didn't have the same number, yeah.
All right, so you've got the CD, it matures in 5 years. You want it to have 5K at the end of those 5 years, and it incurs interest every 12, or it incurs interest every month at a rate of 0.85%. That means today, the amount of money you have to deposit is $4,792.
Yep.
That sucks.
Yeah,
That really sucks. But the point of this is this stuff, this exponential, logarithmic, the differential stuff, all of this whole class, it's full of these types of things that you are going to use in real life. For those of y'all who don't know what a CD is, by the way, it just occurred to me that I might have to define this term. A CD is a certificate of deposit. It's an agreement that you make with the bank that you will loan the bank a certain amount of money, and it will pay you a certain amount of interest off of that money for the bank to be allowed to use that money you gave initially. So it's basically a reverse type of a loan, right? So the bank giving you a loan, you're loaning the money to the bank, and it's paying you interest on that over a period of time. And then it agrees that this contract ends in 5 years. Here's all that money. So having said that, a couple examples. Another example is, hey, certificate of deposit, a CD. This is for 12 years at a rate of 8%. And we want to know how much we have to invest in order to have 15K at the end of those 12 years, assuming a rate of 8% compounded monthly. Plugging everything together, today you would have to deposit $5,761.72, given these conditions. So again, this is really right now just plug and play math. We are, however, at the end of that section, and it is time for another break. I will give you all 10 minutes, come back at the end of those 10 minutes. So at 8:15.